Okay, let us continue the third part of today's class. Okay, please look at the handout of chapter 2. Okay, the first axiom is if n is a neighborhood of x, that is, n is in KLN of x, then x is in n. Okay. In other words, each point belongs to every one of its neighborhoods. Okay. Okay, second, if n is a subset of x and includes a neighborhood of x, excuse me. Then n is a neighborhood of small x. That is, every superset. Okay, we will explain what is a superset later. Of a neighborhood of a point. Small x is in capital X is again a neighborhood of small x. Okay, the third axiom is the intersection of two neighborhoods of x is a neighborhood of x. And the last axiom is any neighborhood n of small x includes a neighborhood capital M of x such that capital N is a neighborhood of each point of capital M. Okay. Okay, I think it is very difficult to understand. Okay, we will give an example later. Okay. Before giving an example, let us see this sentence. The first three axioms for neighborhoods have a clear meaning. Okay. The fourth axiom has a very important use in the structure of the theory. That of linking together the neighborhoods of different points of x. Okay, let us see an example. A standard example of such a system of neighborhoods is for the real line R, okay, where a subset n of R is defined to be a neighborhood of a real number x if it includes an open interval containing x. Okay. And given such a structure, a subset U of x is defined to be open if U is a neighborhood of all points in U. Okay. So we have defined what is an open set earlier. Okay. Now use the open ball. Okay. Do you remember? If you forget, please review the open set and search open set in this handout. Okay. Now we use the concept of neighborhood to define what is an open set. Okay, the open sets then satisfy the axioms given below. Okay. Conversely, when given the open sets of a topological space, the neighborhoods satisfying the above axioms can be recovered by defining capital N to be a neighborhood of small x if capital N includes an open set capital U, okay, such that small x is in capital U. Okay. Okay, originally in reference 125, there will be the definition via open sets following this paragraph. Okay, but due to the time limitation, I think I do not go through too many details in it. If you have time, or if you like, you can refer, you can see, or you can read the reference 125. Okay, problem 27. What is axiomatization? Okay. Solution: the act or process of reducing to a system of axioms. Okay, you can see a reference 126. Okay, next, problem 28. Who is Felix Hausdorff? Okay, why do we need to know who is Felix Hausdorff? Okay, because, okay, let us search for Felix. Okay, Felix Hausdorff appears here. Okay, where is it is the solution to problem 26. What is a topological space? Okay, let us see who is Felix Hausdorff. Okay, solution: Felix Hausdorff. Okay, born in November 8th. Oh, sorry, born on November 8th, 1868, and died on January 26th, 1942. Was a German. Okay, sorry. Okay, was a German mathematician who is considered to be one of the founders of modern topology and who contributed significantly to set theory, descriptive set theory, measure theory, and functional analysis. Okay, due to the time limitation, I do not want to introduce what are descriptive set theory and measure theory and functional analysis. Okay, please see figure 23. Okay, figure 23 shows a photograph of Felix Hausdorff. Okay, it's him. Okay, let us go back to the previous Felix. Okay. Okay, next. Okay, previous. Okay, next, in problem 29, what is neighborhood topology? Okay, why do we need to know what is neighborhood topology? Okay, because, okay, let us search neighborhood topology. Okay, here. Okay, because the neighborhood topology appears in the definition via neighborhoods, and which is the definition, one of the definitions of the of a topological space. Okay, let us go back to neighborhood topology. Okay. Excuse me. Okay, solution: in topology and related areas of mathematics, a neighborhood or neighborhood, okay, note that the U can be deleted, okay, is one of the basic concepts in a topological space. Okay, it is closely related to the concepts of open set and interior. Okay, intuitively speaking, a neighborhood of a point is a set of points containing that point where one can move some amount in any direction away from that point without leaving the set. Okay, please see figure 24. Okay, in figure 24, okay, I need to make this smaller. Okay, smaller. Okay. Okay, in figure 24, it is a set V. Okay, this set V. Okay, in the plane. Okay, is a neighborhood of a point P. Okay, here P. If a small disk. Okay, here is the small disk. Okay, it is a circle. Okay, with its interior, but exclude or delete the boundary. Okay, and centered on the point P. Okay, so if a small disk around P is contained in V, okay, we can see that, okay, the small disk around P is contained in V. Okay, let us go back to the, okay, previous figure 24. Okay. Okay, so let us see the definitions. Okay. First, let us see the neighborhood of a point. Oh, sorry, the definition of the neighborhood of a point. Okay, if X is a topological space and P is a point in X, then a neighborhood of P is a subset V of X that includes an open set U containing P. Okay, so you can see that open set is a very important concept, so it appears many times. Okay, so P is in U. Okay, U is an open set, and U is a subset of V. Okay, V is a neighborhood of P, and V is a subset of X. Okay, and X is a topological space. This is also equivalent to the point P is in X belonging to the topological interior of V in X. Okay, we will introduce what is a topological interior of later. Okay, next, the neighborhood V need not be an open subset X. Okay, this one. Okay, but when V is open in X, then it is called an open neighborhood. Okay, some authors have been known to require neighborhoods to be open, so it is important to note conventions. Okay. A set that is a neighborhood of each of its points is open, since it can be expressed as the union of open sets containing each of its points. Okay, what does this mean? Let us see a figure or also an example. A rectangle as illustrated in figure 25. Okay, let us see figure 25. Okay, figure 25. Okay, I need to make it smaller. Okay, figure 25, we can see there is a rectangle. Okay, here. Okay, with the black boundary and the green interior. Okay, we call this V, and we call this point P. Okay, so figure 25 shows a closed rectangle. Okay, V. Okay, V does not have a neighborhood on any of its corners on its boundary. Okay, for example, the point P is one of the corners of V, and we can see that if we place a disk, okay, which is centered on P, okay, or open ball or open ball on the 2D space or on this plane. Okay, then the disk is not totally contained in V. Okay, so we say that V, the closed rectangle, does not have a neighborhood on any of its corners or its boundary. Okay, similar for any point on the boundary, you can also place a disk here, and you will find that okay, there a part of disk is out of V. Okay, so let us go back to figure 25. Okay. Okay, a rectangle as illustrated in figure 25 is not a neighborhood of all its points. Points on the edges or corners of the rectangle are not contained in any open set that is contained within the rectangle, okay, as we have just seen in figure 25. Okay, the collection of all neighborhoods of a point is called the neighborhood system at the point. Okay, we will see what is a neighborhood system later. Okay, next let us see the definition of the neighborhood of a set. Okay, if S is a subset of a topological space X, then a neighborhood of S is a set V that includes an open set U containing S. Okay, so here S, okay, is a subset of a topological space X, and U, okay, is an open set that containing S, that contains S, and V is a neighborhood of S, and finally X is a topological space. Okay, so we can see that the relationship between these four sets is S is a subset or equivalent to U, and U is a subset or equivalent to V, and V is a subset of X, or V is equal to X. Okay, it follows that a set V is a neighborhood of S if and only if it is a neighborhood of all the points in S. Okay, so you can see that a set V is a neighborhood of S, okay, if and only if it is a neighborhood of all the points in S. Okay, furthermore, V is a neighborhood of S, okay, if and only if S is a subset of the interior of V. Okay, we will introduce what is the interior later. Okay, a neighborhood of S that is also an open subset of X is called an open neighborhood of S. Okay, which is similar to the open neighborhood in the definition of the neighborhood of a point. Okay, so next, the neighborhood of a point is just a special case of this definition. Okay, so next, problem 30. What is topological interior? Okay, why do we need to know what is topological interior? Okay, because we have encountered this terminology, topological interior, in the definition of the neighborhood of a point. Okay. Okay, solution. Okay, first we must understand what is an interior point. Okay, if S is a subset of a Euclidean space, okay, then X is an interior point of S if there exists an open ball centered at X which is completely contained in S. Please see figure 26. Okay, let us see figure 26. Okay. Okay, I need to make this smaller. Okay, and smaller. Okay. Okay, good. Okay, this is figure 26. We can see that there is a set S, okay, which is the green one, okay, S. Okay, the point X is an interior point of S, okay, because we can find an open ball, okay, in the plane. It is an open disk. The center of the open ball is on X. Okay, so X is an interior point of S. Okay, the point Y is on the boundary of S. Okay, so we can because we cannot find an open ball, okay, whose center is on point Y, and the open ball is contained completely in S, in the set S. Okay, so Y is not an interior point of S. Okay, it is on the boundary of X, of S. Okay, so let us go back to the previous page. Okay, this definition generalizes to any subset S of a matrix space. Okay, we will introduce what is a matrix space later. Okay, X with matrix D. Okay, we will also introduce what is a matrix later. Okay, X is an interior point of S if there exists R which is greater than 0, such that Y in S whenever the distance d of xy is smaller than R. Okay. Okay, this definition generalizes to topological spaces by replacing open ball with open set. Let S be a subset of a topological space X. Then X is an interior point of S if X is contained in an open subset of X which is completely contained in S. Okay. Equivalently, X is an interior point of S if S is a neighborhood of X. Okay. Just as we have introduced what is a neighborhood earlier. Okay, let us see problem 31. What is there should be a here. Okay, what is a matrix space? Okay, why do we need to know what is a matrix space? Okay, because we have encountered the term matrix space in the solution to the previous problem. Okay, let us see the Okay, it is 25 minutes. See you next time. Goodbye.